All right. Welcome to class. Happy Thanksgiving week. Just so you all know, so I will not be holding office hours this afternoon from 3:30 to 4:30. I have a doctor's appointment I have to go to, so I'll see you next week after class today. That's not true. I have office hours tomorrow. So if you're around tomorrow, you have questions from 2 to 4 or drop in, you're welcome to come to me. But if you're not, it's totally fine. So let's look at the following. And this question says to rewrite the following limits so that you can use L'Hopital's rule. So all of them are limits where we could use L'Hopital's rule if we rewrote them, but we have to write them as a fraction, right? There's no other way to use L'Hopital's rule unless you have a 0 over 0 or infinity over infinity type, right? Those are the only two times you're actually allowed to use L'Hopital's rule. So none of these qualify currently because none of them are fractions. So we're going to rewrite this first one, and you have a choice. And usually there is one right choice and one wrong choice. So for these ones, especially, you kind of have to make the right choice, otherwise things don't get better. What I mean here is that we have to rewrite this, bringing the e to the negative x down to the bottom as e to the x. So we're going to rewrite this as the limit as x goes to infinity of x squared over, I don't want to write 1 over e to the negative x. I just want to be a little bit wiser about it and write it as e to the x. And then we can apply L'Hopital's rule twice. So if we apply it once, and I know the question didn't say to do that, but obviously we're going to do that. Then we're going to actually use L'Hopital's rule and get the limit as x goes to infinity of the derivative of the top is 2x. The derivative of the bottom is e to the x. We do it again. The derivative of the top is 2. The derivative of the bottom is e to the x. And now as x goes to infinity, 2 over something growing infinitely large is getting closer and closer to 0. As an aside, this would also be a good way of showing that e to the x grows much, much larger than x squared as we go towards infinity. So when you're trying to tell whether one function is growing larger than another one, this is how we do it. We compare them by writing them as a fraction, then taking the limit, usually using L'Hopital's rule. So I'll just point out, this shows us that the words many people like to use is that e to the x dominates x squared as x goes to infinity. It is much, much larger. I will also just mention here that if you had tried going the other direction, meaning if you had tried bringing the x squared down to the bottom instead of the e to the negative x, things don't get better. Meaning, if you keep applying L'Hopital's rule, you actually move further away from having something that's going to resolve itself. What I mean by that is, if we actually rewrote this, I'm trying to find a good split. If I wrote it over here, so if I rewrote x squared times e to the negative x as the limit as x goes to infinity of e to the negative x on top and x to the negative second on the bottom, this is still a type you could apply L'Hopital's rule for. It is a 0 over 0 type. I know it's kind of weird to think about, but e to the negative infinity, right? Think about the graph of e to the negative x, it certainly goes to 0. And x to the negative second, think about the graph of x to the negative second, it also goes to 0 as you move towards infinity. Sorry, I pointed that way. I should have pointed that way. Oh, no, I was pointing that. That's the right way. That's what I meant to be thinking. I was really thinking of the graph of e to the x going to negative infinity as opposed to the graph of e to the negative x going to positive infinity. Same kind of thing though, right? I'm just saying, when I was thinking of e to the negative infinity, I was thinking of this graph going that way as opposed to this graph going that way. But it's the same idea either way. Either way you go, you're still getting closer and closer to 0 as the exponent gets more and more and more negative. But if you try to then use L'Hopital's rule here, you're going to get the limit as x goes to infinity of negative e to the negative x over negative 2 times x to the negative third. And the problem with this is that unlike here, where when you have x to a positive integer power, if you take the derivative enough times, you're eventually going to get to a constant. That's not going to happen when you have x to a negative integer power. It's just going to keep getting more and more and more negative, and you're going to keep having a 0 over 0 type if you keep doing this. This is definitely not the right way to go. And that's what I meant when I said there's like a right way and a wrong way to rewrite this as a fraction. You essentially, the idea is you want the thing that like differentiates more nicely to be on the bottom. I know it's not a very specific criteria, but with enough practice, it becomes relatively obvious. Here, this one actually, there's a couple ways you could do this one. In my opinion, the way I would rewrite this is to rewrite it as the limit as x goes to 0 of x times cosine x over sine x. And really, I should write this as one fraction. The limit as x goes to 0 from the right of x times cosine x over sine x. Yeah. Or I guess I could have written it as x over tangent of x as well, right? That would probably be equal. So here's a counter example to what I just said. Most of the time, there's a right way to do it and a wrong way to do it. Sometimes there's multiple ways to do it. In this case, either way would probably work just fine. Doing it this way is actually probably worse, because if I take the derivative of the top, I'm going to have to use the product rule. It'll still work. If I do that, add the limit as x goes to 0. Let's see, 1 times cosine plus x times negative sine, all divided by the derivative of sine, which is cosine. And if you plug in 0, you get 1 plus 0 over 1. So we get 1 over 1, which is 1. On the other hand, x over tangent would be a little bit simpler, right? The L'Hopital's rule application would give you a 1 over secant squared, and then plugging in 0 for secant squared would also give you 1 over 1. So both would be good there. Whatever feels better. Literally, whatever you see, right? Like I just didn't see it that way until I thought about it. I thought, oh yeah, cotangent is cosine over sine. We should totally write it that way. And often that's true for trig functions, that you're trying to make a fraction happen. You just rewrite whatever your trig function is as its fractional equivalent form. This last one here, I would say you never want to bring natural log of x to the bottom as 1 over natural log of x. Taking the derivative of that is just not good. So in fact, I would almost always say e to the whatever should always come to the bottom because its derivative is relatively easy. And then its inverse function should never end up in the bottom. It's just not nice as an inverse. So here I definitely want to rewrite this as the limit as x approaches 0 of the natural log of x divided by 1 over x. Or, maybe not or. I like to write it as 1 over x. That's just my preference. But a lot of people would prefer to write it as x to the negative 1. Either way, we should be comfortable with knowing that the derivative is going to be negative x to the negative second, or negative 1 over x squared. So using L'Hopital's rule here, it's the limit as x approaches 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared, or negative x to the negative second. But I like writing it like this because then it's easier for me to think about flipping and multiplying. I'm going to rewrite this as the limit as x approaches 0 from the right of 1 over x times negative x squared over 1, which simplifies to the limit as x approaches 0 from the right of negative x, and then we can just plug in 0 and get negative 0, which is 0. Yeah. So when you're trying to apply L'Hopital's rule to a limit after written as a fraction, for these ones where you have essentially a 0 times an infinity, right? Because that's what's really happening in each of these, right? In this first, before we rewrite them, this is something going to infinity times something going to 0. This is something going to 0 times something that's going to infinity or negative infinity. It doesn't really matter, but I am curious. I'm trying to think of the cotangent graph. Oh, of course it's going to be infinity. How do I know that? Because we're a little bit bigger than 0, which means we're in the first quadrant as far as the unit circle would be concerned, and the angles have to give positive values. So it's definitely a 0 times a positive infinity. And then over here, you have a 0 times a negative infinity. But all of these are 0 times infinity types, and we rewrite them by dividing by the reciprocal of one of the two pieces. And then we can almost always deal with it using L'Hopital's rule. The other kinds of things that often require rewriting are the exponential forms. These are all like multiplicative forms. Is not really what they're called, just what I'm calling them right in this moment here. But then you have something like the limit as x approaches 0 of x to the x, or which is a 0 to the 0 type. we talked already, I believe, I'm pretty sure, now I'm less sure because I'm like, did I do it in the other class? I think we talked about the limit as x approaches 0 of 1 plus x to the 1 over x types. How that was going to be e, yeah. That's a 1 to the infinity type. And the third type that is indeterminate, that's an exponential form, is, what is it, James? It's, let me think real quick here. That's going to be negative infinity, that's going to be 0, 0, that's going to be, sorry, I need infinity over infinity type when I do that, so it's got to be infinity to the 0 type. Okay, the limit as x approaches, sure, why not? Infinity x to the 1 over x power. This is a infinity to the 0 type. And all of these are indeterminate forms, right? Meaning it's not just obvious what's going to happen. You might, you could make an argument that 0 to the 0 is almost always going to be 1, but it's not always 1. There's some weird examples where it doesn't turn out to have a limit of 1. Most of the time it is. But these other ones are kind of whatever. All of these require the same process. Doing the e to the natural log thing and then simplifying it until you get something you can use L'Hopital's rule for. So if we look at this one first, well, we're going to rewrite that as the limit as x approaches 0 of e to the natural log of x to the x. And then really when I do this, I kind of think about, I try to remind myself to rewrite the e every time, but I'm really just focused on what's going on with the natural log of whatever. So I know this is going to be the limit as x goes to 0 of, yeah, that's fine. I should have said x goes to 0 from the right because if x is negative, it's problematic. Of e to the x times natural log of x. And then we know that we need this thing up here to be something that's fractional so that we can use L'Hopital's rule. So we're going to rewrite this as the limit as x approaches 0 from the right of e to the natural log of x over 1 over x. And I think we literally just did that limit, didn't we? Right? Wasn't the limit as x goes to 0 of x times natural log of x the one we just did? So we know that that x one is going to end up being 0. I'll still show the work, but it almost feels silly to show the work again. But here we go anyway. It's the limit as x approaches 0 from the right of e to the, we're using L'Hopital's rule for the stuff in the exponent. So it's 1 over x divided by negative 1 over x squared, which ends up being the limit as x approaches 0 from the right, e to the negative x, which is e to the 0, which is 1. So that's the idea with ones like this, is you have to do the e to the natural log and then rewrite the natural log part until it becomes a fraction you can use L'Hopital's rule for. Cool. We could do the rest of these. I don't think we need to do the rest of these. Questions about this or other L'Hopital's rule things that we should be saying, but I am not thinking of saying. You could talk about L'Hopital's rule all day, but we shouldn't, because there's other things like optimization, which I think is the thing that most people would like me to get to. I just wanted to make sure that I cover my L'Hopital's rule basis here, said a few more things about making sure people know how to rewrite things. So optimization. To me, optimization and related rates kind of fall into the same category in that you have to like read a question, often draw a picture and label things that are changing or things that are variables, and then write an equation or two kind of relating the variables or describing the function you're trying to optimize, and then usually take some derivatives, in this case, set them equal to 0. So they have similar flavor, but not exactly the same. Right? Optimization and related rates are definitely different processes, but they have a lot of steps in common. So let's look at some examples. Excuse me, and we'll try to kind of spell out the steps along the way. Optimization. So here is the first optimization problem. A rectangular box with a square base and no top is to be constructed so that its surface area is 108 square inches of material. People often phrase this as, they don't use the word surface area there, they're just saying the amount of material you're using is 108 square inches. But as soon as you see that the amount of something is square inches, or you're like, oh, that's an area. So I know they're talking about the surface area of the box, not the volume of the box or some other measurement of the box. So then we want to know what dimensions of the box will maximize the volume that it holds. And most of the time, the first step is to draw a picture. Step one, draw the box. So great, let's see. It's a rectangular box with a square base. So here's my base that's square. Yeah, I'm drawing it like that. It's fine. And then it has some height. And it looks like I've drawn it just slightly taller than it is wide. So it's not a cube necessarily. It could end up being a cube. But at this point, I know that the length on the bottom, those should both be the same. So I'm going to call both of those X because it's a square base. And then this side here does not need to be the same. So I can give it a different name. We're going to call it Y. Okay. Steps 2 and 3 are to write two equations. You want to, well, I should, that technically, okay, let me back that up. Step 2, what are we trying to optimize? So I want not an equation, but an expression. So I want an expression for the quantity we are trying to optimize. So in this case, what are we trying to optimize? The volume. So great, we know the equation for the volume of a shape like this. The volume is equal to x times y, or x squared times y. And most of the time at this juncture, the thing you're trying to optimize will have more variables than we know how to handle. Right? We don't know how to maximize or minimize a function of two variables yet. You will learn how to do that in 17C. At this point, we are only capable of maximizing a function of one variable. So we need this function of x and y to be just a function of x or just a function of y. So this is where we need step 3, the equation of some constraining fact, or the equation of our constraint. In this case, or in most cases, usually they've told you how much something needs to be. In this case, it's that the surface area should equal 108 square inches. So we know, okay, great. Surface area needs to equal 108 square inches. But we actually need to write the equation for the surface area and make that equal to 108 square inches. So let's see. Surface area shapes like this are not too terrible. It's just all the areas of all the rectangles added up together. So a square is a rectangle, as a reminder. How many rectangles do I have to add the areas up for? In total? Yeah, 5, right? Because it's a no top. So make sure, right, we have to read the question carefully. Oh yeah, there's no top. So the bottom area is x times x, so x squared. And then each of the sides, this front face, this right face, this back face, and this left face, each of those 4 sides has an area of x times y. So I'm going to have 4 times x times y, and that's going to equal 108. Step 4, in your constraint, isolate one of the variables. I want to go back 1 second here and just point out, the thing you're trying to optimize, we don't know what it's equal to. Should not be equal to a number. The reason I'm saying this is because over many years, I've seen lots of people be like, oh yeah, volume equals 108. Not, but just be careful, right? The thing you're trying to maximize, you shouldn't know what number it's equal to yet when you're starting off the problem. Okay, so in our constraint equation, we could isolate either variable, either x or y. Sometimes it's easy, just as easy one way or the other. Sometimes, like this case, it's much easier to make one choice versus the other. So if you see multiple x's and only one y, we should try to isolate y because it's going to be easier. So here we're going to say, okay, 4xy equals 108 minus x squared, and then divide everything by 4x. So y equals 108 minus x squared divided by 4x. And while I could divide each thing by 4x, or write it as like 108 over 4x minus x squared over 4x, and then simplify those, I don't want to do that yet, because I might have an easier time if I plug that back into my other equation first. So now the next step here is to plug that into the thing you're trying to optimize, so that the thing you're trying to optimize is a function of one variable. So we're going to plug in so that in this case, volume is some function of just x. So here we're going to get volume equal to x squared times 108 minus x squared all over 4x. And simplify it. Or really make it easier to take the derivative of in the next step. Because our job after this is to try to maximize this thing, which means find its critical values and then see if they give us a maximum. So I'm going to simplify this by canceling an x here and an x here and saying, oh, I have 1/4, I'm bringing that 4 out in front, times x times 108 minus x squared, or distributing the x 1/4 times 108x minus x cubed. And that's going to be much, much easier to differentiate than the previous versions of it. Sadly, I've not left myself quite enough room. I could try to squeeze it in, but I shouldn't. The wrongest choice. So we just keep going. Step 6. Find the critical values of your function. So we have that v as a function of x is 1/4 times 108x minus x cubed. So now we're going to take the derivative of that. The 1/4 hangs out. The derivative of 108x minus x cubed is 108 minus 3x squared. Set that equal to 0. Technically, we should be checking where it's equal to 0 or where it's undefined, but we know this is a polynomial. It's never undefined. So we're going to get multiply both sides by 4. 108 minus 3x squared equals 0. 108 equals 3x squared. 108 divided by 3 is 36 equals x squared. X equals plus or minus the square root of 36, which is 6. Now, at this point, we should think about what actually makes sense. Right? We're talking about the length of the bottom of this box. X shouldn't be negative here. So our only sensible critical value is x equal to positive 6 inches. And now we get to a place where we have to decide how much work we have to do. So the question is, we found a critical value, great, x is 6 inches. Is that actually maximizing our function? Good question. There's a couple ways. So sometimes the teacher just be more like, the critical value gets going to do the thing you want. And that's typically true. In most of these questions, the way they're asked are such that you're only going to end up getting one critical value, and it's going to do the thing that you expect, meaning this x equals to 6 inches will maximize the volume of our box. That said, in the real world, that's not a guarantee. If you find some function to model some behavior, and you're trying to see where it's maximal, and you just find the critical value, like, well, it's going to maximize it, and you don't check that it's not a minimum, you might run into some real problems. So make sure you check your critical points in general. Here, there's a couple ways to do it. You could either use the first derivative test for maxima. Okay, great. Here's our, let's write things down. So first derivative test. We're going to put our one critical value on there. And if you pick a number less than 6 and plug it into your derivative, you're going to get a positive result. Now, I'm glossing over something here. Technically, if I picked a number that was super duper negative, this value would end up being negative. If you picked a number like -10, -10 squared is 100, times 3 is 300, 108 minus 300 would be negative. So what I really should be pointing out here is that we have an end to our domain here. We should only be thinking of going no lower than 0. Because again, if you think about the domain for this setup here, the least x should be able to be is 0. You can't make a box that has negative inches of length. And similarly, x actually has a maximum value as well in this case, right? You can't make a box where x is bigger than the square root of 108. Because if it was, you'd be using up more than 108 square inches of surface area. Sometimes you have some like artificial domain restrictions. So here, pick a number between 0 and 6, like 1, this derivative is definitely going to be positive. Pick something bigger than 6, like 10, this derivative is definitely going to be negative. So the function would be increasing, then decreasing. So, oh yeah, we definitely have a maximum at x equal to 6 inches. This is not my favorite way to do it. Although I will say in general, if I'm graphing something, I definitely prefer to find out whether my relative extrema are maxes or mins by the first derivative test. Yeah. That's what we're doing. So, sure. So sometimes based on because there's a word I'm looking for. So most of the time when we talk about domain of a function, the domain we talk about is the implicit domain. For example, this function here, x, this function here, before I canceled an x, the implicit domain, or just the regular domain, is just all the values x is allowed to have. So here, x could literally be anything except for 0. But the explicit domain is like the stuff that makes sense. Like if you're talking about a situation where x should be a positive value, then oh yeah, x can't be negative. So here our explicit domain is, well, we know two things. We know that x should be greater than 0. Sorry, you can't see that. And it can't actually be 0, otherwise the volume would be 0. And then we also know that, well, our surface area, which is equal to x squared plus 4xy, is equal to 108. And if you let y be 0 just for a second, then you'd have x squared equal to 108. So the most that x could be would be the square root of 108. If it was any larger than that, we'd be using up more surface area than we had to use. So technically we have a hard stop at square root of 108 as well. This is another reason I don't love doing it this way. It's fine and it works out fine, but people do all sorts of things where they're like, well, yeah. In my opinion, superior way of doing this is to actually use the second derivative test for maxes and mins. So the second derivative test just says, great, find your critical value, take the second derivative of your function, so v double prime of x. So taking the second derivative here, the 1/4 is still going to hang out. And the derivative of 108 minus 3x squared is just negative 6x. And I guess I could simplify that. It's negative 3/2 x. And now we're going to plug in our critical value. So v double prime of 6. I don't actually really care what the value is. I just care what the sign is. The value here would be -9, but I really just care that it's negative. Because if your second derivative is negative, that means your function is concave down. But if you had a critical value somewhere where the function is concave down, it can't be a min, it can't be an inflection point, it had to be a maximum there. So that's the real, in my opinion, value of the second derivative test is for optimization. You can say, oh, I don't want to do something gross to try to first derivative test to see if this is a max or a min. I'm just going to, and again, I will caveat, sometimes taking the second derivative is terrible. And you're like, well, I don't want to do it that way because it's going to suck. But if it's easy enough to take the second derivative, this is what I would always recommend doing to try to test to see if your critical point is a maximum or minimum.
So taking the second derivative test is advantageous. You don't have to worry about the domain.
Yes, exactly. So this shows us that x equals 6 inches maximizes the volume. Okay, great. We spent a lot of time doing that, but we haven't even finished the question yet. Because the question said, what dimensions will maximize the volume? We found x, but we also still need to find y. Fortunately, when you're answering this question, it's almost always easy to go back through your work and find somewhere where you've written y equals something in terms of x. In this case, it's right here. Y equals 108 minus x squared divided by 4x. So now, I'm saying, great, well, if x is 6 inches, y is going to equal 108 minus 6 squared divided by 4 times 6, which is 108 minus 36, so 72 divided by 24, which is 3 inches. So kind of a lengthy process, but the steps are the same. Like with related rates, also a lengthy process, but it's the same like 5 or 6 steps every time. Yeah.
Second derivative test ever fail?
Yes, definitely. It usually doesn't fail for these optimization problems. But yeah, definitely graphing is why I don't like it for graphing. There's a lot, it's really easy to make up functions where the second derivative test fails. Where you plug in your critical point and you get a 0 in the second derivative. Well, you're like, well, it could be a max, it could be a min, or it could be an inflection point, and you don't know until you do more inspection. But for these situations, that's typically not a worry. All right, examples. And we'll try to do some biology ones as well. Just starting off with a few kind of standard ones here. Let's look at this next. Like I did something. What did I do? Sorry, 1 second. I bumped something over here. Okay, all right. Back in business. Let's look at this next one. What are the dimensions of the largest rectangle that can be inscribed in a semicircle of radius 6 centimeters? Wow, you cannot see that at all. Let me unblurify that. I mean, it's not a lot better, but a little better. Meaning my writing is terrible. That's what I meant by that statement. It's not a lot better because it's still hard to read because my writing is poor. Okay, what's that? I can definitely zoom in. But really the better thing for me to do here is to just draw the picture. So when you're asked to optimize something where you're drawing some shapes, it's usually like if you're drawing circles or semicircles, it's usually a good idea to center that circle on the XY coordinate system. So I'm going to draw this semicircle with its center at the origin. So there's my semicircle. It's got a radius of 6. So I'm thinking of this point here as being like 6, 0. This point over here being negative 6, 0. This point being 0, 6. Not super important to label those, but it doesn't hurt. And then I'm trying to inscribe a rectangle, meaning it has to be contained within the semicircle. So I'm trying to, again, want to maximize, right? Maximize? Yeah, largest rectangle, so the largest by area. So I'm trying to maximize the area of the rectangle. I guess I need to like label some sides here. Now, it would probably feel pretty normal to label the base as X and the height as Y. But that's actually a slight disservice to us. So what I actually want to do here is label this point where the rectangle is touching the semicircle as just the coordinates x comma y. Because I've literally gone over x and up y. So I'm going to call this length x and this length y. And then the area of my rectangle is the base, which is twice whatever x is, times whatever y is. So that's what we're trying to maximize. And once again, we see the thing we're trying to maximize is a function of more than one variable. So we need a constraint. Here our constraint is that point that's the upper right corner of the rectangle is touching the circle, the semicircle. So this point, x comma y, also satisfies whatever the equation of the circle of radius 6 would be. Or in other words, our constraint is x squared plus y squared equals 6 squared. And in general, that's a pretty good thing to remember, that if you have a point that's like stuck on a function, it meets the requirement of the equation of that function, right? If you're on the parabola y equals x squared, then great, that's your constraint, y equals x squared. So then we're going to use this to go back here. So in this case, we can solve for either variable. We can solve for x or y. It generally feels more comfortable for most people to solve for y in terms of x so that we're writing things in terms of x. That said, you should also get used to doing it in terms of y. It's good to go, because sometimes it's just nicer in y. But here we'll go against my better judgment and still leave in terms of x. So we're going to say that y squared is equal to 36 minus x squared. And then y is going to be the positive square root of 36 minus x squared. Cannot be negative here because literally the y coordinate is above the x-axis. I should also mention, just as far, we might as well mention the domain stuff here because we're going to talk about it in a minute anyway. So I'll point out that this point here, which has to be in the first quadrant, my x value is bigger than or equal to 0. And what's the biggest my x value could be? Looks like it can't be any bigger than 6, right? If I have to be inside the semicircle of radius 6, I'm limited as to how far to the right I can move. So it looks like here, just to kind of mention the domain stuff off to the side here, it looks like our x value is stuck being between 0 and 6, and our y value is going to be between 0 and 6. Which makes a lot of sense if you look at how y and x are related. Right? If x was 0, y would be 6. If x was 6, y would be 0. And you can't kind of go further in either direction here. All right, so now continuing on, we're going to rewrite the thing we're trying to maximize in terms of one variable. So now our area is going to equal 2x times the square root of 36 minus x squared, or more usefully written as 36 minus x squared to the 1/2 power, so that we can take the derivative. The derivative here is not very nice. No, I'm not gonna pretend otherwise. It's kind of ugly. So let's find the critical values by taking the derivative and set it equal to 0. We have to use the product rule. So it's going to be 2 times the derivative of x is 1 times the other stuff left alone, 36 minus x squared to the 1/2, plus 2x times the derivative of the other stuff, which is 1/2 times 36 minus x squared, the negative 1/2 times the derivative of the inside, which is negative 2x. And we're going to set that equal to 0. And this is definitely where we need to use our ability to factor things so we can actually find the critical values here. I'll do 2 things here. Well, maybe just one thing. I'm going to cancel a 2 here with the 1/2 here. And then I should have done this in the beginning, but I didn't. I'm going to factor out a 2 and a 36 minus x squared to the negative 1/2. So I factor out a 2 times 36 minus x squared to the negative 1/2, always the smaller power of the thing that's occurring. In this first piece here, I'm left with, well, I factored out the 2, so that's gone. I factored out 36 minus x squared to the negative 1/2, so I'm left with 36 minus x squared to the positive 1. Because if we multiply those back together, the powers would add together, and negative half plus 1 is positive 1/2. Over here, first of all, I'm going to notice that there's a minus sign there, so I'm going to put that in front. So it's going to be minus, and then I'm left with an x. I'm left with an x. I factored out a 2. Oh, 2 x's. Sorry. I would have x times x. Thank you. Yes. So not 2x, but x times x, which is x squared. Thank you. I was missing the x squared there. I was like 2x. I factored out the 2. What are you talking about? You're totally right. Thank you. Okay. Now we're going to rewrite this. We're going to bring down this 36 minus x squared to the negative 1/2 to the bottom. So it's kind of a positive power. And rewrite this as our numerator. 36 minus x squared minus another x squared is minus 2x squared, all over the square root of 36 minus x squared, or 36 minus x squared to the 1/2 power. And then, yeah, there's a times 2 out here. Not really important. Set that equal to 0. Technically, we could also consider where it's undefined. It is undefined when x is equal to 6. But I think we can all see with our eyes that if x is 6, what's y going to be? And if x is 6 and y is 0, what's the area going to be? 0, which is definitely not maximal. So although x equal to 6 is technically a critical value, we're just going to kind of ignore it. Okay, so setting the top equal to 0 and dividing by 2, we have 36 minus 2x squared equal to 0. 36 equals 2x squared. 18 equals x squared. X is equal to the positive square root of 18. Because we know that x doesn't get to be negative here. And if you wanted to simplify that a little bit, you could say that x is equal to 3 root 2. And here's a great example of where I wouldn't use the second derivative test because taking the next derivative is going to be terrible. So there's a couple ways to do this. And actually, I should have, I'm curious about something here. Yeah, that's fine. Yeah. So I'm annoyed by this type of problem in general because there's so many ways to test to see if you actually have the thing that you're supposed to have. So we could use the second derivative test here. I don't want to do that. We could use the first derivative test here, which is totally valid. This is why we talked about the domain a little bit up here. So looking at the first derivative test to check if it's a maximum. Well, we're going from 0 to 6. Our critical value is root 18 or 3 root 2, which is between 0 and 6, right? Root 18 is definitely smaller than the square root of 36, which is equal to 6. Picking a number bigger than 3 root 2, so I'm going to pick 5. How do I know 5 is bigger? Well, root 2 is about 1.4. 3 times 1.4 is about 4.2. Or really, root 18 is less than root 25, which is 5. Now, here's where I would cheat. I know it's supposed to be a maximum. Great. Look, it did what I thought it was going to do. Increasing, decreasing, maximum. I definitely checked. You saw me do it, right? Right? You all saw me do it? Right. But if you actually want to check, okay, if we plug in 5, 5 squared is 25 times 2 is 50, 36 minus 50 is negative. And then the bottom is always positive. So yes, plugging in a 5 right there gave me a negative derivative. Similarly, plugging in a 1 over here, 36 minus 2 is positive, the bottom is positive, the whole thing is positive. But you can kind of get away without actually checking. The other way people do this sometimes is they use there's like a test for absolute maxima that says it has to, wait, it's the extreme value theorem stuff, where you say, okay, great, we know we have an absolute maximum either at the endpoints or at the critical values. You know, if you plug in 3 root 2, the whole thing's going to be positive in your original function. Or if you plug in 3 root 2, you get a positive thing here, a positive thing here. If you plug in 6, you're going to get 0 as your area. If you plug in 0, you're going to get 0. So of the 3 values, 0, 0, and something positive, which one's the biggest? Oh yeah, the something positive. That's nobody's preferred way of doing this, I will say. Like nobody likes doing it that way. I don't know why, it's less loved. So we did the first derivative test, we got a maximum, great, and then finally, we have to go back and do the last thing and find the other dimension. Now be careful here. Sometimes these questions get asked, what is the maximum area? Sometimes these questions get asked, what are the dimensions to maximize the area? Make sure you're answering the question that is asked. So here, they're asking us for the other dimension, right? Let's see, what are the dimensions? Yes, what are the dimensions? So we found X, now we need to find Y. So Y is going to equal the square root of 36 minus X squared. That's going to be the square root of 36 minus the square root of 18 squared. Now this one's extra silly because my dimensions aren't the square root of 18 and the square root of 18. Because the height is the square root of 18 and the base is double the square root of 18. So my dimensions are actually, the base is 2 times the square root of 18 and the height is the square root of 18. Questions? Comments? The checking part is always the part that drives me a little bit crazy, honestly. Like, okay, we have to show there's like a million ways to check this thing. I would again say, I recommend the second derivative test if it's easy to take the second derivative. Otherwise, I'd probably go to the first derivative test. I will point out the first derivative test only really works if you only have one critical value, which I think they talk about in the textbook here. I want to mention it just so that I'm not saying something that is totally out of line. Yes, so on page 288 of your textbook, you have the first derivative test for absolute extreme values. Basically, if you have one critical value on an interval, if it's a maximum, then it's an absolute maximum. Because if you think about this here, right? Here, the function's always smaller before my critical value and always bigger afterwards, and that's the entire domain, so that's all that can happen. Yeah, okay. Let's do another one. One more of this kind of, I think of these as like shape questions, like we've got shapes and we've got things inside of it. Like I said, I know it's just the category that sticks in my head. These are all questions about shapes. They do it again. Okay, sorry. This document camera here is very, very finicky. Yeah, let's see. So let's say we want to construct a cylindrical can. Cylindrical, I'm sure I'm not spelling that right. Cylindrical, yeah, the Y comes before the L. Cylindrical can to hold a volume of, let's make life not too terrible here. 100, yeah, I think 100 is usually good. 100 pi cubic centimeters. Oh, wow. Okay, let's try that again. What dimensions of the can will minimize the amount of surface area required, or the amount of material, probably metal, required to construct the can? With 3D shapes, it's usually you have this much surface area, maximize the volume, or you want this much volume, minimize the surface area. Those are the two kinds of things that happen with three-dimensional shapes typically. And let me read that again because I see some of you being like, what did you write? We want to construct a cylindrical can to hold a volume of 100 pi cubic centimeters. Why the pi there? Because it makes the math easier for the problem. What dimensions of the can will minimize the amount of material required to construct the can? So in other words, this is a volume of something, minimize the surface area. But we should draw the can first. Sometimes I phrase this question as a cup instead of a can, because a cup has an open top and a can has a closed top. Like, so what I'm thinking of here is like a can of refried beans. That's what I'm actually imagining. Is like, what dimension should the can of refried beans have so it holds this much volume, and I've used the least amount of metal to make it. So great. Well, I don't know what the dimensions are yet, so I'm going to label this part R and this part H. And if I'm trying to minimize the surface area, I want to minimize surface area. Well, the area of the bottom circle is pi r squared. The area of the top circle, question, sorry. That's a good question. Yeah, you should assume it's included if they don't say it's not. Yeah, so if I say I have a cylindrical shape, unless they, yeah, right, because if I said a cup, right, to me it's obvious. So really, the person writing the question should be specific, is really the truth. They should specify explicitly if it's open or closed. But if they just say a shape that seems like it's obviously closed, then it's closed. But yeah, I certainly, if I was writing this, I would write a closed top can if I was actually trying to do like. So the surface area, the bottom circle is pi r squared, the top circle is also pi r squared, so I have a 2 pi r squared. And then the around part is a rectangle. I always think of this as a roll of paper towels. And if you take one paper towel that goes all the way around and you unroll it, what shape do you have? A rectangle. And the rectangle, right, if you unroll the paper towel, the rectangle still has the same height, but what's the length? 2 pi r, right? Because you've gone all the way around the circumference of the circle. And so this area here is 2 pi r h. Okay, that's what we're trying to minimize. Then we need our constraint. We are constrained by the fact that the volume should be 100 pi cubic centimeters. So here our volume, and the equation for volume is the base area, pi r squared, times the height, should equal 100 pi. One of the reasons I've decided to do this problem is because in this problem, you still have some, but you have far less domain restriction than you might realize. Here, you could have a can that looked, I mean, you could have a lot of cans that look really stupid. You could have a can with a tiny radius that was super duper tall that would have the right volume. Or you could have a can that looked like a pancake that was super duper wide and very, very flat. And both of those cans could hold the right amount of volume and would definitely not minimize the amount of material you're using. But the point I'm making here is that your radius can actually be any positive value. So both your radius and your height are somewhere between 0 and infinity. But if you make a can that looks stupid enough, you can have your radius be as large as you want it to be. Okay. What that really means is that we can't try to show that we have a maximum or minimum based on that last criteria that I said nobody really likes. Right? We can't plug in the endpoints because we don't have a closed interval here. We couldn't use the extreme value theorem to check if our thing is going to give us a max or min. Totally fine. We got other options. Okay. So there's a constraint. Obviously, I'm going to solve for the height here because I don't want to, right? If I have a choice here, I'm going to solve for the thing that's a little easier. So I'm going to get that the height is equal to 100 pi divided by pi r squared. And obviously, I should cancel a pi and write this as the height equal to either 100 over r squared or 100 times r to the negative second, whatever seems like it's better for you. Plug that back in to the thing we're trying to minimize. So now my surface area is equal to 2 pi r squared plus 2 pi r times 100 times, I'm going to go with this one here because I'm going to simplify this. I don't want to use the product rule if I don't have to. So let's simplify this as 2 pi r squared. 2 times 5 times 100 is 200 pi. And then I have r times r to the negative second is r to the negative first. And as you can see with this function, if I wrote this as 200 pi over r, you'd be like, oh yeah, r can't be 0, but r could definitely be any positive value. Technically, r could be any negative value, but we know that doesn't make sense in the context of the problem. Explicit domain versus implicit domain. Implicit is literally any number you can plug in and get some result. Explicit is the numbers you can plug in that make sense to be able to plug in. Okay, so let's find those critical values. I should amend that. Let's hopefully find the critical value. We really are only hoping for one critical value. So take the derivative, you get 4 pi r minus 200 pi times r to the negative second. Set that equal to 0. And while technically here, the safer way to solve this is by factoring out a 4 pi r to the negative 2. The more typical way of solving this is to bring something over to the other side of this equation. I would rewrite this as 4 pi r equal to positive 200 pi divided by r squared. I'd multiply both sides by r squared and divide both sides by 4 pi. So I have 4 pi r cubed equal to 200 pi. And then divide both sides by 4 pi, I get r cubed equal to 50. So r is equal to the cube root of 50. I think this looks like a situation where the second derivative test would work out just fine. So if I take my second derivative of, yeah, I feel bad. I was like, I didn't write my derivative. I didn't write a derivative here. I feel kind of bad about that. So I should have written surface area prime is equal to that. And then my second derivative here would be 4 pi plus 400 times pi times r to the negative third. And if I plug in the cube root of 50, I'm going to get 4 pi plus 400 pi times the cube root of 50 cubed to the negative third. Sorry, not to the third. And I'm going to stop because at this point, I can tell it's going to be positive, right? There's nothing negative in this. Okay, technically there's a negative power, but that's not going to change anything sign, right? Cube root of 50 to the negative third power is going to be something positive. It's going to be 1 over 50. Times 400 pi is still positive, plus 4 pi is still positive. So this is definitely positive, which means we're concave up, which means we have to have a minimum. As we expected to get, or as we were asked to find. Or we could have used the first derivative test. We're almost done, but again, almost done is not all the way done. We still have to find the other thing. Right, there was an h to find, right? Because they said, well, actually, I should check. We want to construct a solution. Okay, what dimensions? Okay, what dimensions they can will minimize the amount of material. So we know that r should be the cube root of 50. And then we go back and we look for where we have h equal to something with just r's in it. Oh, right there. So we're going to plug in r there and check this out for a second, because I do think this is kind of worthwhile. Sorry, I know I'm squeezing something in. It's terrible. So the height is going to be 100 divided by the cube root of 50 squared. What I really want you to see here is that I'm going to rewrite 100 as 2 times 50, and the cube root of 50 squared is 50 to the 2/3 power. And then 50 divided by 50 to the 2/3 is just 50 to the 1/3, which is the cube root of 50. So check it out. You get 2 times the cube root of 50. So what I think is interesting here is that if you're trying to minimize the surface area of a can, you want the height and the diameter to be the same. Because the height is twice the radius, but twice the radius is also the diameter. So you ever see those cans in the store, the bigger cans of refried beans? They look kind of like a square, like they're about as high as they are wide. They did their math. They were minimizing the amount of material that they were using so that it costs less to make the can and still hold the most amount of volume. So yeah, again, now that said, a more complicated problem would involve the fact that it probably costs more for something on top versus something on the side or vice versa. So we can do a different question where we're trying to minimize, instead of the amount of surface area, the amount of cost by making the amounts of things cost different based on the square area. But let's not do that. All right. Are we optimized out? Too much optimization? Yeah. Do we know no more? We should stop. Call it a day. We can. I mean, we could stop. We don't have to stop though. I got a couple more problems though. So let me ask you, is there anything else you would like to see before we end class in 20 minutes or less? Yes. Yes, I can. Let's see, what do I got? I've got a few different things here. Let's take a look. Oh gosh, it's always so messy. Yeah, okay, we're going this one. Let me actually let's look in the textbook here before I get too here. Oh wow, I'm just getting water all over the place here. Sorry. So we could do that one, but let me just double check one thing here. All right, yeah, let's look at this one, even though it's a little bit weird. This is problem number 28 from section 4.4. Here's the setup. I'll try to write this so you can read it. The energy expended by a fish swimming at a speed of v against a current of speed u is E as a function of v equal to a times v cubed times L divided by v minus u. Double check and make sure I'm not writing something silly here. Nope, that's right. Okay. So the one thing I'll say about this specific problem, and a lot of the biology problems in general, is a lot of the setup is already being done for you, right? We're not having to interpret a question or set up the thing we want to maximize or find a constraint to make it a function of one variable. We're just often given the thing we're trying to maximize or minimize. So here, we're then asked to, one, what swimming speed minimizes the energy expenditure of the fish? Expenditure. And just before we do that, let me ask, if we're thinking about swimming speed, what's the natural domain or the explicit domain for the swimming speed of the fish? Could it be 0? Yeah, maybe, right? The fish is just chilling, not swimming hard, like just like. Could it be negative? Not if we say the word speed. If they said the velocity, then technically, yeah, direction matters. We're just talking speed, and they already kind of gave us a direction, right? They told us that we were swimming against the current. So we kind of have this direction, and it doesn't really make sense to consider going in the opposite direction. So here I would say that we're thinking about the swimming speed v being greater than or equal to 0. It wouldn't make sense for it to be negative in this context. Another problem it could. So we're trying to minimize the energy expenditure. We're trying to minimize E by doing the usual thing, finding the critical values and seeing if it gives us a minimum. So we're going to take the derivative. So this is where it's really important to remember what's your variable and what isn't. The only variable here is v. Everything else is a constant, which is a little annoying, but it's what we've got. So I would probably rewrite my function here as everything on the top. So a times L times v cubed over v minus u. So now if we take the derivative, usual quotient rule stuff, it's the bottom, v minus u, times the derivative of the top, which is a times L times 3v squared, minus the top, a times L times v cubed, times the derivative of the bottom, which is 1, all divided by the denominator squared. And if we're going to set that equal to 0, it's really going to be in our best interest to try and factor out as much as possible. And I see a lot that can be factored out. From both of these two terms here, we can factor out an A, we can factor out an L, and we can factor out a V squared. Doing that, we're going to be left with, let's see here. So if I factor out an A times an L times a V squared, I'm left with still a V minus U times 3 minus a V all over V minus U squared. Simplifying this, I get A times L times V squared. This is going to be 3V minus 3U minus V, but 3V minus V is 2V. So it's 2V minus 3U all over V minus U squared. Almost there. So I see, well, so that's interesting. Okay. I see, how many critical values do I see? If I'm setting this either to be equal to 0 or undefined. What's one potential critical value for sure? Yeah, well, yes, kind of, but I'm trying to trick you a little bit. But thank you for giving me that. But yes, I would say for now we're going to say v equals u is a critical value that we're going to consider. So v equals u. And then if we set the top equal to 0, you're either going to get v equal to 0 or 2v minus 3u equals 0, which means v is equal to 3 over 2 times u. Okay, I want to point out this is a trick because v equals u isn't in the domain of the original function. You go back to the original function and say that v is equal to u, you're going to get division by 0. If you're swimming exactly the speed of the water, apparently that's going to require an infinite amount of energy expenditure. Which seems kind of weird, but I guess it's because you're exactly, like you're maintaining place exactly in the right, I don't know. I mean, I don't know enough biology to really know what's going on here, so okay. But that is going to be not something that we're going to, yeah, we saw, but so this is actually a good question. It's great because even though v equal to u isn't a true critical value, right? You can't have a maximum or a minimum there because you have a vertical asymptote essentially, right? Going towards infinite energy expenditure. You still have to include that on your first derivative sign chart. So when I start trying to figure out what's going on here, I definitely don't want to use a second derivative test. If I use my first derivative test here for my well, I have 0 over here, which should be the end of things. And then I do need to think about including u on my sign chart because it is a place where things can change. And then we have our actual critical value that's going to matter, which is 3/2 times u. And here's the hard part about this. Oh yeah, question.
Less than, closer to 0 than v.
I don't. But there's no v on here. Right? All these values are in terms of u. We have v equal to u, v equal to 3/2 u, v equal to 0. But you're right, I can't be putting v on here because v is our variable. So the hard part now is, what do you plug in to test if the thing is positive or negative? Well, everything has to be in terms of u. So if I'm trying to go bigger than 3/2 u, I'm gonna pick twice u. So if I plug in 2u over here, well, let's see, if I plug in 2u, let's check it out. So again, u is positive. So I get a times L, and so I should back up a second. You definitely want to pick the more factored form to plug into. That's why we do the factoring part of that's also good to find about it. But I should plug in over here. So a, did they say a is positive? No, but everything should be positive, right? We're talking about energy here, right? If this is our energy equation, A should be positive, V should be positive, L should be positive. Interesting. Okay. So twice u, positive, 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 and 2 times 2u is 4u minus 3u is still 1u, which is positive. So positive, 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 and the bottom is for sure positive. So over here, my first derivative is positive, so my function is increasing. Between u and 3/2 u, okay, so that's 2u over 2 and 3u over 2. So that's 4u over 4. That's 6u over 4. I'm going to try 5u over 4 because that's in the middle. Or maybe easier to think of between 1u and 1.5u, I'm going to pick 1.25 u. My 5/4 is 1.25. So right here, we're going to try 5/4 u. Or I could have been smarter about it and said, I know that my 3/2 u came from this factor. This factor is raised to an odd power, which means we should expect the sign to change. Well, let's check. I plug in 5/4 u, positive, 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 and then 2 times 5/4 is 5/2, and 5/2 minus 3 is negative. So it is going to be negative there. Decreasing over here. And then over here, if you pick a number less than u, like half of u, positive, 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 negative. So it's negative over here as well. So it looks like if the fish swims at 1.5 the speed times the speed of the current against the current, that will minimize the energy expenditure. Interesting. So V equal to 3/2 times U minimizes the energy expenditure.